I think we're ready. Okay, this is the session on code-based cryptography, September 28th. Our first speaker is going to be Andre Esser, speaking on the paper Hybrid Decoding Classical Quantum Trade-offs for Information Set Decoding.
Thank you very much for the introduction. So, can you hear me?
Yes, we can hear you.
This is joint work with Sergi Ramos Caldera, Emanuele Bellini, Jose Ignacio Latorre, and Mark Manzano. As we all know, we are in the transition. Why does this slide not? Okay, as we all know, we are in the transition to the use of post-quantum secure cryptography to protect against large adversaries with large-scale quantum computers. But before we arrive in the era of large-scale quantum computers, we are likely to have access to small quantum computing devices where qubits are still a very limited resource. And even if we have algorithms that might only need a polynomial amount of memory, this might mean they still need millions of qubits, which are just not instantiatable on these devices. And like this, it's the case for information set decoding algorithms, which are like the tool for assessing the security of code-based systems. So in this work, the goal was to construct hybrid algorithms which use qubits, so hybrid algorithms that work with a classical coprocessor, and then they do not obtain the full quantum speedup, but still they want to obtain some quantum speedup. Before we dive into these hybrid algorithms, let us cover some basics on the synonym decoding problem, set decoding algorithms, which solves the synonym decoding problem. So for the synonym decoding problem, we are given a parity check matrix H, R rows and N columns, and a syndrome, a vector of length R. Everything is binary, so we're working in F2, and we're given an integer omega, which is the error, and to vector E, which fulfills H times E is equal to S, and it has a Hamming weight of omega, meaning the number of ones in E is equal to omega. And we will represent this compactly like this: H times E is equal to S. So information set decoding is a technique to solve this problem introduced by Prange in 1962. There are several advancements after Prange's algorithm, but most of them use an exponential amount of memory, so we stay with Prange's algorithm here. And how does this algorithm work? So imagine we would know a set of n minus r zeros in the vector E. So here they are represented in the beginning and in the end just for easier illustration, but they could distribute anywhere over this vector. And then, of course, these parts of the matrix here are not relevant in the matrix vector product because they are multiplied by 0. Then we can also remove them from this matrix. And then we are left with this R times R square matrix, which represents a linear system, which we can solve via Gaussian elimination. And so we can recover this vector, this orange vector here, and then we can put in the zeros wherever we remove them. And if this vector now is of weight omega, we're done. We found the solution to the synonym decoding problem. But this vector is not necessarily of weight omega because we don't know such a set of zeros in the beginning. So what we have to do is we have to guess a set of zeros, but since omega is usually pretty small, guessing zeros might not be too bad of a strategy. And then we guess another set of zeros until this vector is of weight omega, which means we found the solution. This is how Prange's algorithm works. I don't want to cover in detail how the quantum circuit for this algorithm works, but what we need to know is what is the input to the quantum circuit? So what is necessary for the quantum circuit to perform this algorithm? Before we talk about this, just that you can relate somehow what can we expect from a quantum algorithm. If the algorithm you've seen runs in time t, then the best we can get, or the best what is known, is a square root speedup. So it's basically a Grover search over this set of a subset of zeros of the vector. So the best we can hope for is the square root of the running time. And what's the input to this quantum circuit? Well, besides some auxiliary informations, it's basically this matrix, R times N matrix. And what we show in the paper, not in this talk, but in the full version of the talk, we showed that this matrix, that if you perform to transform this matrix into a systematic form, then it is sufficient to input A to the quantum circuit to perform this algorithm. And this means that we basically need n minus r times r bits to represent this instance on the quantum circuit plus some auxiliary informations. So this is basically the baseline for our trade-offs. And now let us talk about the hybrid algorithm. So in the paper, we give two different algorithms and a combination. We will cover combination. These slides were intended to come later, but okay, let's close. So first, we need a performance measure for our trade-off. So how do we measure the performance? So, well, our trade-off should interpolate between the classical Pranger, which works with 0 qubits and time complexity of t, and the quantum version, which we've seen works with n minus r times r qubits and a running time of square root of t. And then we want to interpolate between both endpoints via the hybrid version, which works with delta times n minus r times n qubits. So delta is smaller than 1 here in the optimal case, and time complexity of t to the small t of delta. Let's quickly check that both endpoints fall into this model. So delta equal to 0 is the classical Pranger, where we have then the small t of delta is equal to 1. And for the quantum Pranger, we have delta is equal to 1 and t of delta is equal to 1/2, because the running time is square root and it needs all the qubits. Okay, how does our hybrid algorithm work? Basically, we've seen that if we know such a set of zeros in E, then we can basically discard this part of the matrix. And if we know this a priori, we could discard this part from the matrix before we input it to the quantum circuit. So what we will do is we will guess such a set of zeros and shorten the code in these alpha coordinates, or by these alpha coordinates, to reduce the input to the quantum circuit. And what we can also do is we can puncture the code, meaning we just disregard some of the rows of this matrix. If we disregard some of the rows of this matrix, and there is some zero submatrix appearing, which of course we can also disregard. But this also means we discard some coordinates of the error, and the error might have some weight in these positions. So we also reduce the weight of the error by puncturing the code. On the downside, we might introduce multiple solutions here, because we're discarding parity constraints of the matrix, so basically the information on the syndrome. So we might have to run our quantum circuit multiple times. So the algorithm, in summary, works by first randomizing the instance to trying to get this weight of p into this gray shaded area, shorten and puncture the code, apply the quantum circuit on the rest of A, which is left multiple times to collect all the solutions. And if none of those solutions solves the initial instance, we start again with a randomization and shortening and puncturing. Overall, this matrix A is then this green frame part is insufficient to input to the quantum circuit. Now, this formula for the qubits is not very relatable, so let's put this into the frameworks that we've just seen: the qubit reduction factor delta on the x-axis and the time exponent t of delta on the y-axis for different settings here, coding things such as the full distance and the half-distance setting, but also cryptographic settings like the Mac-Alice and Byte HQC setting, meaning in these settings the relation between the number of rows and columns of the matrix and the error weight is different. And as a sum, you say that the less or the smaller the error weight, the better these trade-offs behave. We can also check for a qubit reduction factor of 1, all of them interpolate to the quantum version with a time exponent of 0.5. And for a qubit reduction factor of 0, we all end up with a classical running time of t to the 1. And the smaller the error weight, the better the trade-off. This has something to do with the ability of puncturing the code in many coordinates without introducing multiple solutions. So in summary, it's weight and rate sensitive, and in summary, we give with trade-offs which still obtain significant quantum gains, and they are most effective for low weight. They give a continuous interpolation between the classical and the quantum version of Pange's algorithm, which supports near and mid-term realizations. Thank you very much, and the paper is online if you want the details.
Okay, if there are any questions, you can post them on Zulip. Right now, I don't see anything posted right there. We have a few minutes though before the next talk needs to begin. Yeah, we'll see if anybody posts a question for you. But thank you for the talk. Yeah, at some points the audio, at least for me, was a little bit interrupted, but not enough that it was a problem for understanding. It was clear enough for understanding, but there was some issue.
Was it a technical problem or was it background noise? You mean?
I believe it was maybe a technical problem because it would be a tenth of a second interruption. It would just stop for like a tenth of a second. So it was easy to understand you, but it didn't sound quite perfect. I don't know that anybody else had a different experience, or maybe that was just me. Oh, Tanya's saying she had no noise problem, so it may be something on my end, actually.
Okay. But did you also see this long break between switching of slides?
I didn't notice that.
Okay, because for me it always took like a second until the next slide appeared. But,
well, maybe it did. Maybe it did, but the way you were speaking, it seemed to go smoothly. I believe. Okay, I don't see any questions still on Zulip, so maybe we can at least get prepared for the next talk. So we'll need to switch who is sharing here.
Take yeah, did already.
Boyan said he did have noise problems, so I'm not sure what the issue is. Not sure what the issue is, but hopefully, and maybe Boyan can say something else. I don't think that it was something severe enough to make it a problem for understanding. Okay, yeah, I don't see any questions posted here in Zulip, so maybe we can switch presenters. I'm still seeing the conclusion slide.
All right. Yeah, I see.
Yeah. Okay. Here we go. Okay, so our next talk is how to backdoor classic McAleese and how to guard against backdoors. And this will be presented by Karl Richard Schneider. You can go ahead.
Yeah, hello and thank you. This is joint work with Tobias Hemmert and Johannes Mittmann from the German Federal Office for Information Security and Alexander May and myself from the Ruhr University Bochum. And in our paper, we contribute the first, at least to our knowledge, backdoor for McAleese-like crypto systems. And we also show that this backdoor is applicable to classic McAleese, at least in the case of uncompressed keys. And we also show that there is a really simple countermeasure for this backdoor. And at least to our knowledge, we also present the first backdoor, which uses post-quantum cryptography for the adversarial instance. So we remain secure even in the cases where cryptographically relevant quantum computers are available. So now let's first think about what we expect from a backdoor. We would expect some transformation or modification of, in our case, first a simplified McAleese-like crypto system, where the adversary is able to substitute the implementation used by the user. So, for example, somewhere along the supply chain, the adversary is able to substitute the used implementation. And we want that this modification of the crypto system is indistinguishable from the original system, but still leaks some secret secret information that is only accessible for the adversary A. So we want some exclusive access for the adversary here. And the goal here is that the adversary learns some secret information that allows them to recompute the secret key of the user. And that's now what we want for a backdoor, but we also need a crypto system that we can backdoor. And for this, we discuss a McAleese-like system that we call vanilla McAleese, which is basically a schoolbook-like McAleese system. And there we start with the typical key generation that you'd expect, where we have an invertible matrix S, the parity check matrix of your code H, and the permutation P. And their product is the public key, while the components themselves are the secret key. And what we do now is we do not sample them directly from random, but we incorporate some seed delta, and we derive all these values from that seed delta. So this delta is actually a good compression for all of these three values, because the whole key generation is deterministic in this value. And you might also notice that we use the Niederreiter version here, but this is not relevant because for the backdoor, we will focus on that permutation and do not use any special properties of that code. So now we have the key generation, and to backdoor it, we want to embed this delta, this small representation of the secret key. We want to embed this seed into the public key so the adversary can learn it. And to do this, we first start by generating the matrix S and the code with its parity check matrix H from delta. And now we modify how we choose the permutation. And in this case, we start by sorting the columns of S times H lexicographically to create some kind of fixed point that the adversary can use later. And now the critical step is to use that delta encrypted under the adversary's public key that is somewhere embedded in that substituted implementation, and use that ciphertext to select one permutation of that n factorial possible permutations. And as before, we have our matrix S and H. And for the permutation, we then use the combination of those two permutations that we chose, which is, again, a permutation. So we now have a backdoor public key, and now the adversary gets access to that public key because, well, it's the public key and it can be distributed as you wish. So now the adversary starts from that public key and again sorts the columns of the public key lexicographically. And at this point, note that you do not recover the first permutation, that P prime, but you recover by sorting, you recover the inverse of that permutation selected by the ciphertext of delta. And because we now know this permutation, we can learn the ciphertext, decrypt it with the secret key of the adversary, and learn the original seed delta again. And then we simply rerun the key generation with the sorting of the columns of S times H to learn the full secret key. And by this, the adversary learns the secret key. So now we now must discuss whether this is actually a backdoor. And for this, we refer to the framework used by Adam Young and Moti Young for setups, which are a formalism for these backdoors. And the first property is that all of these inputs for functions in the modification need to be identical. This is obviously the case. We just modified how we select the permutation and do not introduce any other inputs. For example, we only modified the key generation and do not introduce any other inputs. Then we also need to make sure that the encryption is efficient, and for the encryption for the adversary instance remains efficient, so that the key generation overall remains efficient. And this is also given here. we also need exclusive access, which is given by the use of some asymmetric scheme. And the outputs remain compatible because, as I've described before, the permutation that is chosen to create this vector is still a permutation. So in the terms of using the terms from Adam Young and Moti Young, this is a strong setup, which is only distinguishable for the adversary who can always resort to trial decryption. But this is only under the assumption that the ciphertext itself is indistinguishable from random, which is a bit stronger assumption than the classical INCPA assumption. But because this sorting and coming back to this fixed point can be done by every party, the ciphertext can be seen by every party. So to remain indistinguishable, the ciphertext itself needs to be indistinguishable from random. And now we can discuss how we protect against this. Well, the first idea that might come to mind is just throwing away the concept of using a seed delta and sample all the matrices from randomness, as I've described in the first, at the first slide for the key generation of that vanilla McAleese. Well, the problem here is that assuming that we have some decent pseudo-random functions, we can, the setup, so the backdoor implementation could still resort to using one of these. And we additionally lost the reproducibility because we do not have any value that generates the sampled matrices anymore. But also notice that for this vector, we heavily rely on this delta because it's really small. And as the whole key generation is deterministic in delta, this also allows to verify the key generation with a different trusted implementation. And for this different and more important trusted implementation, it also doesn't really matter whether it is especially efficient or whether it runs on the platform that we want to use. The only important thing is that you trust it because the seed, in this case, serves as a witness that the key generation was without a backdoor, just due to the deterministic nature of the key generation. So, and this brings us to an advice for everyone who implements McAleese-like crypto systems and also, wants to standardize them, that if the delta is part of the secret key and has to be stored along with it, then only weak setups are possible, which in the terms of Adam Young and Moti Young means that the user is actually able to detect the backdoor, in this case by rerunning the key generation. So now we've seen a fairly simple instance of McAleese. We now want to discuss how this translates to the classic McAleese NIST PQC submission. So I won't cover the whole submission here, but only the relevant differences. The first one is that the matrix S is chosen in a deterministic fashion, so that S times H starts with the identity matrix, so that we only need to transmit the second half of the matrix. And we also focus here on the systematic form, while some parameter sets generally allow for cases where the identity matrix here is not entirely given. These are called semi-systematics, but we don't focus on them for simplicity here. And it's also important to know that, as I mentioned before, that the seed delta is actually part of all key truncations in that submission. So only weak setups are possible, where the user or the owner of the legitimate secret key can actually detect this backdoor. In the submission, this was motivated because they want to allow for key truncations, where you trade off storage space for recomputation time, because in the end you only need that delta to regenerate the full private key and to decrypt messages. Furthermore, there is no explicit permutation P. But this actually is not a problem because the submission also fixes the code to binary Gopher codes. And if we have a short look at them, the only important things to notice here is that we have two different types of values, this G, this Gopher polynomial, which is the same for all columns. And it's also important to notice that these alphas, these supports of the code, are only relevant for one column each. So in the end, we have an implicit permutation just by the ordering of these alphas. And this allows it this allows us to apply this modified backdoor permutation simply to the ordering of these alphas, and the backdoor translates rather trivially. So now it's also worth discussing what we can use for instances for the encryption of the adversary. And for these, we needed this indistinguishable from random of the ciphertext. And this is provided by a randomized Niederreiter crypto system from 2008. And for our paper, we decided to instantiate it with category 5 code parameters from the classic McAleese submission, which would result in a ciphertext size of around 1,600 bits. And we now need to ensure that this actually fits into the public key. And yeah, actually, this does fit without any problems because the smallest classic McAleese parameter set already allows for permutation selection string of around 27 kilobits. So we can actually have to pad this ciphertext with random data to uniformly select a permutation for the smallest parameter set. And for the category 5 parameter set, this grows to around 73,000 bit. So there's plenty of space for example, post-quantum ciphertexts. So what have we seen now? Well, we've seen a backdoor for McAleese-like crypto system, which generally abuses the deterministic key generation, but by knowledge of that seed that is used for this deterministic key generation, this backdoor can also be easily prevented. And especially we have so big public key that can be used to hide data that we actually can instantiate it with McAleese itself. So we do not need any additional assumptions on the hardness of the scheme for the adversary. Well, an open question here is obviously whether this translates to other code-based schemes, for which, at least for Bike, I don't really have an answer. For HQC, For HQC, I actually don't see a way to do exactly this backdoor, but a rather simple other one. And so we don't know whether this translates to other code-based schemes that don't have permutation in that way. And I also want to stress the advice again that it's important to actually store these seeds to make the keys verifiable, especially if you're implementing it and noticing that that the seed is not necessarily used anywhere again. Yeah. And with this, I'm done. Thank you for your attention.
Okay, thank you. Thank you. That was very interesting. Okay, there is a question. Victor Duchesne says in the Zulip module, if I understand correctly, thanks for the talk, he says, thanks for the talk. If I understand correctly, the countermeasure you suggest is only available to the person who generates the key. You cannot verify that there is no backdoor if you only know the public key. Would there be a possibility for anybody to verify that the public key is properly generated with some kind of zero-knowledge proof embedded in the public key, perhaps?
Well, actually, that's something I've thought about before as well, because you do not necessarily have access to that seed delta. For example, in the context of hardware security modules or smart cards, one of the ideas is that the secret key never leaves that device. And for these, I think some kind of zero knowledge proof would be nice to have to make it backdoor free. But in a sense, it's especially important for the owner of the secret key to have it backdoor free, at least in most scenarios that I can think of, rather than that any other person knows that it's backdoor free. But in general, if it's possible to construct a zero knowledge proof in some way that that there is a seed delta that generates exactly this secret and also public key, then yeah, I don't see why this wouldn't be possible.
And Tanya also has a question. You highlighted that you don't need any extra assumptions. Would you even have space for, say, a Kyber ciphertext?
Well, this is pretty much visible in this table. I actually don't know exactly the size of those Kyber ciphertexts right now, but I think the 27 kilobits for the smallest instance are actually is actually the data rate that you can hide inside the public key. So I think if the ciphertext is smaller than 27 kilobits, you actually can hide it inside there.
And we have another question from Freja Elbro. Do you think it would be possible to create a backdoor to Michaelis that cannot be fixed by storing the seed?
Well, that actually depends on what you consider the Michaelis system, because in the way I've described both of them, the vanilla Michaelis and the classic Michaelis one, the key generation is actually described as being deterministic in that seed delta. And what we're using as a countermeasure is exactly this determinism, so that if you know the seed, you know, at least if you trust the implementation that you use to regenerate it, or maybe you have enough time to compute it by hand, that you actually get the same private and public key that you would expect from the specification. This is kind of similar to the known answer tests that are commonly done, because there you also have a completely deterministic function, and you just provide some known good values as inputs and outputs, and use that to verify your implementation. And but in this case, it's actually not known answer test, but a test that you can run with a different implementation for you, for your specific key. So I don't see how, without making the key generation not deterministic, such a backdoor would be possible. So it should be a rather generic countermeasure.
Mm-hmm. And then I have one last very brief question. Because of the naming of it, you chose vanilla Michaelis, and I was wondering if there was a joke in there about Coca-Cola, because you have classic and you have vanilla. I wonder if that came to mind, or if that's just a coincidence.
That's just a coincidence, but a really nice one. No, the actual reasoning behind that was that we originally wanted to use the term schoolbook Michaelis, but there's actually no schoolbook Michaelis version where you use the Niederreiter version and you use some seed to generate the values. In the schoolbook versions, you typically find all the three values are actually randomly sampled. And as we deviate a bit from that typical schoolbook description, we decided to use another name simply.
Okay, well, thank you for that. All right, we probably need to switch now to the next speaker, which is, let's see. Okay, the next speaker actually is Victor Dissin. So if we can switch to get him on board. Okay. Okay, there you are. Okay, so Victor Disserin will now present the third talk. Yes, third talk in the session. LRPC codes with multiple syndromes, near ideal size chems without ideals.
Thank you, Daniel, for the introduction. So my name is Victor Disserin. I'm a PhD student at the University of Limoges in France. And I will present to you a joint work with Carlos Aguilar-Melchor, Nicolas Aragon, Philippe Gabory, and Gilles Zemmour, called low-rank parity check codes with multiple syndromes, near ideal size chems without ideals. So behind this quite long title, I'm going to present to you a new code-based key encapsulation mechanism in a rank metric, which is a different metric than the Hamming metric, which has interesting properties, in which you see the distance as the rank of a certain matrix. It works with masking of low-rank parity check matrix, which is a special type of low-rank parity check codes in the rank metric. And our scheme can be instantiated with or without ideal structure, meaning that the public key can have or not redundancies inside the matrix. And it leads to very competitive parameters, even without the use of an ideal structure. So just to see how our work inserts inside existing code-based cryptography. So I've described here the different possibilities when constructing a code-based key encapsulation mechanism. So you can choose between the Hamming or the rank metric, and your public key can be structured or unstructured, as I said before. And you have also a third dimension, which is you can have masking, meaning that it's more like a Michaelis-like crypto system, or you can have no masking between the public key and the secret key, meaning like you are in the Aleknovich-like crypto system. And so far, only 5 of 8 possibilities were fulfilled when you take the round 2 NIST code-based candidates. And with this work, so we present 2 additional possibilities in rank metric with masking, either with structured objects or with unstructured objects. And I would also like to point out recent results on multiple syndromes RQC and the unstructured version, which do more or less the same as us, but with no masking. So to go more in detail on how our new chem works, I would like to present first existing LRPC-based cryptography. So it's like it's very much similar to a Michaelis crypto system. So for the key generation, you have the secret key, which is an ideal low-rank parity check matrix. So a low-rank parity check matrix is the parity check matrix of rank metric code, which has very interesting properties. And the public key is the masked version of the secret key, meaning the systematic form of your secret key. Then to encapsulate a shared secret, you choose a random error in a support of small dimension R, and you send the ciphertext to be the syndrome associated with your error and the parity check public key matrix. And to decapsulate your shared secret, you take the syndrome and you multiply it by the left block of the secret key matrix, and you get then this time the syndrome associated with the error E, and this time not the public key matrix, but the secret key matrix. And this is very useful to use what is called the rank support recovery algorithm, which in the case where you have an LRPC matrix U and an error E, it's very efficient to find the support of the error E. And then you can recover your shared secret. So the problem of that framework is that the rank support recovery algorithm has some failure rate in the decapsulation. And so in Rollo, which is so the NIST candidate based on LRPC cryptography, in Rollo, if you want to have competitive parameters, so it's a Rollo 1 flavor, your decoding failure rate is quite large, around 2 to the power minus 30. And if you want to decrease this decoding failure rate down to something negligible, which is something below 2 to the power minus 128 bits, then you need to increase your parameters, and the scheme which is called the Rollo 2 flavor is as a result less competitive. And so we are going to improve in our paper these parameters of Rollo 2, but while keeping a negligible decoding failure rate. So the core idea is to send what is called multiple syndromes at once. So for the key generation, it does not change. So you still have your secret key to be low rank parity check matrix. But this time it can be ideal or not, depending on which instance you choose. And the idea is for the encapsulation, you will send several syndromes at once. So you will pick L random errors. L will be a parameter of your crypto system. So you choose L random errors in the same support E, where E is your shared secret, and you build L different syndromes, H times EI, where the errors have the same support, and you send these several ciphertexts, these several syndromes at once. And then for the decapsulation, you will do as before, multiply the ciphertext by matrix A, and then you will have several syndromes, but this time with the secret matrix U as a parity check matrix, and you have several syndromes with the same support. And then the rank support recovery algorithm you can use is the same to recover the shared secret E, but this time you have multiple syndromes, so it's more efficient. So if you look at the slide, you can think that we only multiplied the ciphertext by L, and then the performance will be less efficient, because if you don't change the key and you multiply the ciphertext L by times L, then it's a longer, your parameters are longer. But the advantage here is that because you have a better decoding failure rate, you can decrease the parameters, meaning the size of your secret key and public key matrices. And then overall, even if you have the ciphertext which is longer, you will gain overall on the sum of the public key and the ciphertext sizes. And so because of this new idea of sending multiple syndromes, the rank support recovery algorithm is more efficient, and we are precisely able to give an upper bound to the decoding failure rate. And the proof is detailed in our paper. And so the decoding with several syndromes can also be seen as the decoding of an interleaved code, which were presented in a 2019 paper by Renner, Yarkovitz, and Bartz. So with our new idea, we are able, so as I said before, to reduce the parameters of flavor Rollo 2. And so the public key size is reduced, but not the ciphertext size, or very, very little. because we, of course, pay the price of sending multiple syndromes at once. So only the public key size decreases. But what is interesting here is that the gain on parameters are enough so that we can lift the ideal structure on our crypto system, and we are able to suggest parameters of an instance with no ideal structure and still be competitive. And so if we compare to existing attempts on CAMs, so here I present two comparison tables. So the first one on the top of the slide is a comparison between unstructured post-quantum key encapsulation mechanism, and we can see here that we are top performing in that category. So, for example, we are 3 times better in size than a Frodo-Chem unstructured lattice attempt. And the bottom part of the table is a comparison between structured code-based key encapsulation mechanism, and here we are slightly better than others. And as compared to lattices, we are not better than lattices. So our approach is specific to the rank metric, because in Hamming metric, sending errors with the same support would be less efficient. You can only send a smaller number of multiple syndromes before you have an attack. And also, our approach is specific to LRPC decoding algorithm and cannot be adapted naively to other classes of codes. So in our paper, we prove the indistinguishability under a chosen plaintext attack of our crypto system, and it relies on 2 assumptions. So the first one is the difficulty of the indistinguishability of a random matrix and a systematic form of an LRPC parity check matrix. And the second difficult problem is the rank support learning problem, which was introduced 5 years ago, which is a variant of the syndrome decoding problem in rank metric, and with several syndromes of the same support. So to conclude, we presented a new rank metric crypto system with competitive parameters and no ideal structure, which is a guarantee, an additional guarantee of security. So we proved precisely the decoding failure rate based on the probabilistic result on the support of the product of 2 random matrices, which is interesting on a mathematical point of view. And for future perspectives, we have additional ideas to improve the algorithm to reduce the size of the parameter M of about 10%. And there are also recent results on the generalization of our results to other rank-based crypto systems. Thank you for your attention, and I will be pleased to answer any questions.
All right, thank you. Pardon me. First of all, I want to say that the question session for the previous one, I pronounced this name Freja, but I think it's probably more likely Freya. So maybe somebody can correct me on that in Zulip. I want to say your name correctly. I think it's probably Freya Elbro. I don't see any new questions in Zulip, but I have a couple of questions. Maybe I can ask briefly. Is the limiting attack for this with the parameters you have going to be something like a min rank attack with some optimizations for rank codes?
Yeah, so the limiting attack on our crypto system is exactly like a limiting attack against the rank syndrome decoding system. And as shown in existing literature on algebraic attacks on the rank syndrome decoding, it's like algebraic attacks similar to the ones which are on the min rank problem. So yes, it's correct.
And also I wanted to ask, does it make a difference for that, or could there be a variant of that that's using extra information from sending multiple syndromes at once?
So actually, that problem, so it could be, it could happen that you, like sending multiple syndromes can add extra information to lead to an attack, but this problem was studied in a recent paper by Bardet et al. And Brio, I think, which was called algebraic improvements on attacks on the wrong support learning system problem. Sorry, and in that paper, it shows that for some range of parameters, you gain extra information with multiple syndromes, so that you can have an efficient attack. But we were careful in our design to avoid this like range of parameters, so that the attacks, we are obliged to use the state-of-the-art attacks against the rank syndrome decoding problem with only one syndrome, and that there is no impact on sending multiple syndromes. So.
Okay. All right. Well, thank you. Thank you. We are just a little bit behind schedule. We should probably switch to the next speaker now. The next speaker will be, yes, Anmol Porwal. If you are available, we could get you ready and set to go. And Freya says in Zulip, much better, thanks. Okay, I can see you. Okay, there your slides are. Okay, so let me introduce you. So Anmol Parwal will speak on interleaved pranga, a new generic decoder for interleaved codes.
Thank you. So this is a joint work with my co-authors, Lukas Holzbauer, Hidong Leung Liu, Julian Renner, Anthony Wagdutse, and Violetta Weger at the Technical University of Munich. So the goals of our presentation is to understand the complexity of attacking interleaved crypto systems, and I will explain what interleaved crypto systems are in a bit. But attacking interleaved crypto systems is the same problem as doing genetic decoding of interleaved codes, and so we will be looking at ways of doing genetic decoding of interleaved codes. And in doing so, I will also explain a new algorithm called interleaved pranga. Okay, so let me first explain what interleaved codes are. So an L interleaved code word is just a concatenation of L code words from constituent code C. So what that means is that you have a constituent code C, and from that you just take any L code words and you concatenate them and put them in a matrix. So this would be one L interleaved code word. Now the reason this construction is interesting to look at is because it turns out that for many interleaved codes, you can efficiently correct many more column errors than the error correction capability of the constituent code that you're looking at. And in particular, these things, interleaved decoders also exist for interleaved Gopher codes. So the idea here is to actually apply this to the Mikuli system, and so that's how you kind of can get an interleaved crypto system. So what he would do is that in this, Bob would encode, instead of one message, he would encode L messages, and he gets L code words, and then he puts them in a matrix as the rows of the matrix, and then he just adds T column errors to that code word matrix. So you could do that by adding an appropriate error matrix that has T non-zero columns, and that's how he gets the ciphertext. And then Alice can use an interleaved Gopher decoder to decode R. So this is how this would look like. You have your code word matrix. You just have L code words in it, and then you just add an error matrix that has a T non-zero columns, and adding them together gives you your ciphertext. Now, because this is an interleaved Gopher code, what that means is that the number of column errors that you can add is generally going to be greater than the error correction capability of the Gopher code that you're using. So this would suggest that the security level of the system would hopefully be larger than what you would get, would be larger for the same key size. But in order to be like sure of that, I mean, so we do have so the number of column errors is greater than the number of errors you would typically have in than the number of errors you have in the regular make-believe system. But because these are column errors now, it's not entirely obvious whether you do get a benefit. So it's important to understand whether it's how difficult or what's the complexity of solving this problem is, which and the problem being like given R, what exactly is the code with matrix, or in other words, doing generic decoding of interleaved codes. Okay, so I will describe I will describe 3 algorithms to do that. So these 3 algorithms, we call them random ISD, CF-based strung, and interleaved Pranga. So I will first quickly explain what the first 2 are. So random ISD is very simple. The idea is that you just take any row from your ciphertext receive matrix. You just take any row, and that row will have at most T errors. So you can just run a classical information set decoding attack on it. So here you can use any classical ISD algorithm like Pranga or Stern. And in general, you are not restricted to just rows. You can take any linear combination of the rows if you want as well. So because any linear combination will also have at most T errors, and in each iteration you can just pick any random row or any vector from the any non-zero vector from the span of R. So that's random ISD, and that's probably the simplest way of doing that, of doing generic decoding. Now the second algorithm is so here note that if you were to concatenate the generator matrix and the received matrix, then the code spanned by this, that's generated by that, is going to be the same code that is generated by the generator matrix that you get by concatenating G and E. So what you can essentially do is you can just run a low weight code finding algorithm on the code that you get by the concatenation of G and R. And so you can, for example, use Stern's algorithm here. And then finally, you have interleaved Pranga. Now, before I explain how interleaved Pranga works, I should say that in a sense, you could say that the CF-based algorithm using Stern can be thought of as like the best algorithm for doing generic decoding of interleaved codes, at least so far. So I mean, it has like the lowest complexity. So it would also be interesting to compare interleaved Pranga with CF-based Stern. Okay, so now let me explain how how interleaved Pranga works. So first, what you do is like you concatenate G and R, just like you do in the CF-based algorithm. And now let's just assume all the errors, all the column errors are confined in this red region. So just for simplicity, we assume all the column errors are right next to each other. So now the first step is that you pick any k plus l columns at random from this matrix. So let's, again, for simplicity, assume they are, let's say, just the first L columns. So it's this blue part here. And now this is going to form a square submatrix. And then the next step would be to check whether this square submatrix is rank deficient or not. So you want to check whether this square submatrix is whether it's full rank or not. So the reason why we want to do that test is so if you, for example, look at the erroneous part of R that is inside the blue submatrix. So here, now it might be the case that maybe one row is like completely error-free. If that is the case, then so one row in the bottom part that is inside this submatrix is completely error-free. If that is the case, then this is going to be rank deficient. And then by using like the re-encoding step of Pranga's algorithm, you can decode this entire row. So this would reveal at least some of the error positions. And in general, you're not. It might also be the case that maybe some linear combination of R, some linear combination of the rows of R has a completely error-free part in the blue submatrix, and then that would also actually work. So that's the idea. So that's like the very high-level gist of it. Okay, so for the comparison, I will show some plots comparing the asymptotic exponents of these algorithms. So before I do that, I should also mention that so with respect to the interleaving order, that is how many code words you have in one matrix, and so that I denote by L, and T is the number of erroneous columns. You generally don't want L to be very large, or in particular, it should be smaller than T, because it turns out that there is an efficient tag on interleaved crypto systems if L is at least T. But you also don't want L to be very, very small, because doing interleaving is what gets you a better error correction capability. So it shouldn't be too small either, and there needs to be a bit of a balance. Okay, so now the plots. Now here I wanted to only look at the CF-based plot, which is the red curve, and the interleaved plot, which is the blue curve, because they are really the main competitors here. So on this plot, you will see that generally the CF-based drone algorithm is generally better, unless you're looking at very low rates. And this is for L equals to T over 20. Now, however, if you were to increase L a bit, so now it's T over 10, then you see interleave Pranga seems to perform a bit better, but still, at least for high rates, CF-based drone is still better. And then if you're willing to increase it even further, so if you're willing to increase L to, let's say, about 20% of T, then now generally interleave Pranga is better, unless we are looking at very high rate codes. Before I conclude, I should say that for the proposed for the parameters, for the finite parameters that have been proposed so far in the literature, generally their parameters are closer to these ranges. So L is close to about T over 20. And they're also generally high rate codes, like at least 0.6. So in that case, CF-based drone is indeed better and would determine the security level for those parameters. But I should say that, but there have not been that many proposed parameters for interleaved systems. So it might still be possible that there are good parameters, but in ranges that are closer to this, in which case interleaved Pranga would also be, it would be important to also take that into account. Okay, so that brings me to the end of my talk. We looked at looked at why it's important to understand generative decoding of interleaved codes, because it's important to assess the security of interleaved crypto systems, and also this is also just an interesting problem from just a coding theory point of view. And interleaved Pranga is potentially competitive. At least it beats CF-based drone in certain parameter ranges asymptotically. And this technique of checking the rank, so for future work, it might be possible to apply this to other decoders like Librickle or Stern, in which case we might get something that is better than interleaved Pranga. Yeah, so that concludes my talk. Thank you.
Okay, thank you. I'm not seeing any questions yet in Zulip. If you have any questions, please post them on Zulip, and maybe we can take them up later. We're a little bit behind schedule, and I'd like to catch up here at the end. So thank you, Anmol, very much. Maybe we can get the next speaker on board here with the slides. So the last speaker for this session, I believe, is going to be Daniel Hast. Yes, he's coming on board now. So Daniel Hast, I'll give you a moment to get your slides up before I introduce you.
And Sarah Arpin will be giving the second part of the presentation.
Oh, okay, okay. Yeah. Okay, thank you. Okay, so
whoops, we are at a later slide there. Let me go back to the beginning.
Okay, so here we go. So Daniel Hast and Sarah Arpin We'll be presenting our last presentation for the day, a study of error floor behavior in QCMDPC codes. All right, thank you.
Hi, thank you. Yeah, I'm Daniel Hast. I'm a postdoc at Boston University. So this is joint work with Sarah Arpin, who will be giving the second half of the talk, Tyler Billingsley, Junbo Lau, Ray Perlner, and Angela Robinson. And this started as a collaboration at the Rethinking Number Theory Conference the summer before last. This concerns the bike crypto system. Regarding what is bike, so this is a code-based key encapsulation mechanism based on quasi-cyclic moderate density parity check codes. I'll say more about that in a minute. It's one of the 4 remaining key encapsulation mechanisms in round 4 of the NIST PQC process, 3 of which are code-based. So the question, the sort of main sticking question about, or one of the main questions, is about NCCA security. And so the issue is there's a known attack that exploits decoding failures. So in order for it to claim NCCA security, the decoding failure rate has to be exponentially small in the security level. So let's go into more detail on what is the byte crypto system. The secret key is a parity check matrix, and it's quasi-cyclic in the sense that the 2 blocks are both circulant matrices. It's moderate density in the sense that the row weight of the secret key is on the order of square root of n, so square root of the message dimension. And we have parameters for the block length, the row weight, the error, the weight of the error vector. And so the public key is, some sort of scrambled version of this. The message is encoded as an error vector, the ciphertext is the syndrome, and it's decrypted using this black-gray flip iterative decoder. And the key thing about these iterative decoders is that it can be kind of hard to do like a direct analysis of decoding failure rates, so often this has to be accessed through various forms of simulation or other estimation. And in particular, low to moderate density parity check codes with these iterative decoders, they display what's called an error floor phenomenon. So as the block length varies, while leaving the other parameters fixed, we have a rapid decrease in the decoding failure rate in a waterfall region, but then it switches to linear and plateaus in this error floor region. And so in order to accurately estimate decoding failure rates, we have to account for this error floor phenomenon. So for LDPC codes, there are certain graph theoretic techniques using something called the Tanner graph that work for analyzing these decoding failure rates. Unfortunately, that's not feasible for MDPC codes. So there's a couple approaches that have been used to try to study these before. Baldi et al., they show that there is indeed an error floor phenomenon. And Vasseur defines 3 sets of near code words and low weight code words and analyzes their impact on the decoding failure rate. And in particular, this leads to some lower bounds on the DFR, though, of course, for the perspective of the security, we kind of upper bounds are what we're ultimately going for. And now let me say a few words about what is our approach to this. So what we do is analyze, essentially, to better understand this error floor behavior, we run some computational experiments and simulations at the 20-bit security level. Because if you go all the way up to 128-bit security, right, the sort of cryptographically relevant range, these things are, it's infeasible to find any decoding failures. So what we do is we use the byte design parameters to generate parameter sets for the 20-bit security level. We use the BU shared computing cluster to run some highly parallelizable experiments, and then we investigate what are the factors that contribute to decoding failures and affect the error floor. And so we're running things in this iterative loop where we sample random keys, reject certain known classes of weak key, sample random messages, run the decoder, and see if there are decoding failures. So let's take a look at the results just in terms of the sort of raw DFR as a function of this block size. So we can see here for these given parameters, we have indeed, as expected, a sort of quadratic region where the waterfall region, where a quadratic fit is the best fit, and then it abruptly shifts to a linear fit with a much lower slope in this error floor region. And so here we can actually experimentally observe the error floor. So for the rest of our results, I will hand it over to Sarah.
Great. Thank you, Daniel. So I'll just continue to talk here a little bit about our experiments and exactly what we observed about the DFR at the 20-bit security level. So first of all, we wanted to compute DFR on these special sets of code words that had been previously identified by Vasseur as likely to cause decoding failures. So we computed these sets. Of course, there are varying weights. So instead of actually computing the decoding failure rate on these sets, Vasseur defined a notion of distance that we can use to say our code or our input error vector is blank far away from the set Cn or 2n. To take a look at the results of that, along our horizontal axis, we have a distance from the set to 2n, n, and c, so code words and near code words. For very small distances, you can see that there were quite a lot of decoding failures, and as that distance increased, the decoding failure rate sort of ended up about at the average that we computed for random error vectors of weight 18 is the t weight that we were using for this particular R value. So we can see and confirm here that at the 20-bit security level, these sets are actually causing decoding failures. However, when we computed the decoding failure rates of our generic vectors, the error vectors which caused decoding failures were not overly close to Cn or 2n. So here we looked at our decoding failure vectors from the random simulation that Daniel showed you, and we also computed distances from Cn to 2n and 2n of randomly generated error vectors. So it's a little bit hard to see. Hopefully these axes are visible, but these ranges for number of overlaps with Cn and 2n are not extremely different between the decoding failure vectors and the randomly generated vectors. So maybe there's some other classifying behavior that we can look to sort of single out vectors which might be likely to cause decoding failures. Here again, you can see another experiment that we ran on our random vectors versus our vectors which cause decoding failures. So this is another distinguishing feature that we were looking at, and it was the syndrome weight of the error vectors themselves. So in the red plot, you can see generic vectors, of course, of the correct weight t, and their syndromes, average syndromes across our varying R values that we computed the DFR for. Of course, the sort of relevant waterfall region is right there around R equals 600, give or take. So you'll notice that starting after the waterfall region, you can really see a difference in syndrome weight between the error vectors which cause decoding failures and generic vectors of weight t. So here we also computed the syndrome weights versus overlaps with the sets identified by Vasseur, the code words and near code words. You can see that as the number of overlaps with one of these sets increases, the syndrome weight goes down. So that is to be expected. But we're still seeing, so above, we have our average syndrome weight. That's the green dotted line. And then the black dotted line is the average syndrome weight for a decoding failure vector. So again, we're seeing these number of overlaps are not very large or large enough to really single out these decoding failure vectors. So for our conclusions, we verify the waterfall and error floor DFR picture at the 20-bit security level for BIKE. We've looked at these sets Cn and 2n and corresponding collections of vectors which are close to these sets, and we've found that they are not overly represented among the decoding failure vectors at the 20-bit level. So decoding failure vectors do have lower than average syndrome weight, but being close to Cn and 2n is not really enough to distinguish a vector which will cause a decoding failure from a random vector. So for our next steps, we're going to try to extrapolate and see where the error floor might begin at higher security levels. We also want to find other ways to classify error vectors, which might be likely to contribute to decoding failures. And we're also, looking to see what happens during the iterative bit flip decoding process. Maybe one of the error vectors gets brought closer to the set Cn and 2n during this process somehow. And we're also looking at tanagraph techniques to classify error vectors that might cause decoding failures. And with that, I will say thank you. And our paper is posted and also on the proceedings for further detail. Thank you.
All right, thank you. I don't see any questions yet in Zulip, but I can ask something. These results you have at the 20-bit security level, I'm wondering what is do you have a measure of the statistical significance of your results? Well, whatever you have to say here.
Statistical significance of, well, we have a few statistical tests, but I'm not sure it's exactly what you're asking about. You mean to extrapolate towards cryptographic parameters? Yeah, with that, we just kind of have this heuristic idea that scaling down the security level and the parameters along the BIKE, they have parameter recommendations, should scale the DFR as well. I believe other papers have used this sort of style of scaling down parameters to examine things more closely that can't really be reached at cryptographic size.
Okay. Yeah, I'm not seeing anything else yet in Zulip. Where do you think this puts you? Okay, there's something coming up, but I'm asking something else, so I'll ask it in a second. Where do you think the future goes with this in terms of coming to a conclusion with BIKE and saying, oh, our analysis is tight enough that we can trust that we're safe at cryptographic strength? Do you think that there's an end in sight that your work is leading toward? Or does it seem that that's a fundamentally difficult problem and that it may be far in the future for coming to a conclusion?
I mean, the way that I think of our results is that it indicates that there's, need to improve on the existing analyses and extrapolations, right? It shows that, very likely the known classes of near code word that are known to cause decoding failures aren't sufficient to of decoding failures, and so it doesn't really let us draw a solid conclusion on the decoding failure rate, but it does let us kind of say, well, we need to find new classes of error vector that lead to decoding failures to get a more complete classification, right? So hopefully that will be able to lead in the future to more solid conclusions on the security of BIKE. At the moment, and maybe Sarah, you'd have more to say about this, but that's how I think of it, at least.
Yeah.
Yeah, I agree. I just think that maybe we need more theoretical results on the location of the waterfall region, and that, the point where you switch from quadratic to linear in your decoding failure rate graph. A more solid understanding of that at cryptographic size would be important.
Okay, Victor Disserin says in chat, or asks in the Zulip chat, do you have an intuition on why there are two distinct error regions, waterfall versus linear?
Personally, I don't, which was part of why this project was so interesting to me, is that this graph shape is a real mystery, right? So that point where it changes is a mystery. We were lucky to have hit it with our parameters, and I think a greater understanding would be helpful.
Yeah, if I recall correctly, I think for LDPC codes, this has been a little better studied, and it has something to do with there's some connection to graph theoretic properties of the Tanner graph that's driving this phenomenon. I'm actually less familiar with what's going on with the LDPC code picture, but yeah, so I think, the literature on Tanner graphs for LDPC codes should have some stuff on why this occurs, at least in theory. But, the issue for MDPC codes is quantifying when this occurs is, seems to be a computationally difficult thing. So, yeah.
And also, your idea moving forward for testing if during bit flipping, right, for decoding, if you get close to these sets, do you have any evidence for that you've seen so far, or is that kind of a shot in the dark? You think it could be something, but you haven't observed anything like that? Do you have any evidence that actually is a fairly likely route forward for analyzing these errors?
We haven't yet experimentally analyzed the bit flip decoding process itself, but I guess it was a conjecture by one of our team members, just a shot in the dark, that it might be something like that, because, you are switching your vector fundamentally during this process, and it's sort of all done behind the scenes. So we would like to maybe go back and look at the log for what is happening for these decoding failure vectors.
Okay, well, thank you. I don't believe we have any other questions now, but I'm sure that if you have questions, you can contact the speakers and get answers to them offline. So, there is another question. Let me hold on just a second. Scott Fleur asks, as for the reason for two separate regions, the obvious reason is that there are two specific reasons the decoding algorithm fails, and one reason is quadratic in the block size, the other is linear. Yeah, I don't know what he's talking about, but I hope that you do, being more knowledgeable than me in this. But anyway, we're well over on time. Yeah, just a comment, yeah. We're well over on time, so let me conclude this, and thank you to all of the speakers in this session, and to Andreas and the speakers in the first session as well today. And I want to remind everybody that we will reconvene tomorrow at 11:30 UTC to start the multivariate cryptography session. So thank you for attending. I'll see you later.